going to continue with the topic of exponentials and logarithms B, and we're going to look at further logarithmic equations. Now, when we've looked at exponential and logarithms earlier in the course, we looked at basic logarithmic equations, so this is just taking this a wee bit further with the three new properties of logarithms that we have now learned. So we're aware of these properties here and should be able to use these like we did in the last lesson, but we should be able to use them in equations as well. So many mathematical models of real life situations actually use exponential and logarithmic functions. So that's why we need to be able to solve equations involving logarithmics. And like I've already said, we've previously studied the basic logarithmic equations, so we can now look at further equations. So the first example, we want to solve log to the base a of 13 plus log to the base a of x equals log to the base a of 273, where x is greater than 0. So on the left hand side, we can see that we're adding two log terms, both with the same bases, so that means we can multiply the arguments. So on the left hand side, we'll have log to the base a of 13x, and that is equal to log to the base a of 273. Now we can see here we're working in log to the base a on both sides, so that it then follows on that 13x is equal to 273, and we can divide throughout by 13, and that means that x is equal to 21. So just now would be a good time to pause the video and take this example down, and then come back for example 2. Okay, welcome back folks. So let's look at example 2 now. We want to solve log to the base 11 of 4x plus 3 minus log to the base 11 of 2x minus 3 equal to 1. And we can see here that x is greater than 3/2. So that's the domain of this equation here. So you can see in the left hand side that we're subtracting two logarithmic terms, and they both have the same bases, so that means that we can combine these terms and we can divide the arguments. So log to the base 11 of 4x plus 3 over 2x minus 3, and that's equal to 1. Now remember, if we have an equation written as a logarithmic equation, we're able to change that to an exponential equation. So we've got the base here is 11, our exponent is 1, and our argument is the fraction. So 11 to the power 1 is equal to 4x plus 3 over 2x minus 3. Now, to start solving this, we can multiply throughout by 2x minus 3. And we can expand the left hand side here to get 22x minus 33 equals 4x plus 3. I can now add my 33 to both sides and subtract my 4x from both sides, and that will leave me with 18x equals 36. And finally I can divide throughout by 18, and that leaves me with an answer of x equals 2. So just now would be a good time to pause the video and take this one down in your notes before coming back for a further 2 examples. Welcome back folks. So example 3 this time, we want to solve log to the base a of 2p plus 1 plus log to the base a of 3p minus 10 equals log to the base a of 11p, and we know that p is greater than 4 for our domain. So again, you can see in the left hand side that we have got two separate log terms adding together, and they both have the same bases, so we're able to combine these. So log to the base a of 2p plus 1 times 3p minus 10, and we can expand those brackets there. But we can also say that we can see that we've got log to the base a on both sides of the equation. So we can say that these two brackets here are equal to 11p, and that means that the expansion of those brackets is equal to 11p. So 6p squared minus 17p minus 10 is equal to 11p, and I can subtract my 11p from both sides to give me 6p squared minus 28p minus 10 equals 0. Now before I start factorising that, I can see that I can divide throughout by 2 to make my factorisation a little bit easier. So dividing throughout by 2 will leave me with 3p squared minus 14p minus 5 equals 0. When I factorise that, I'll get 3p plus 1, p minus 5 equals 0. And by the null factor theorem, each of these brackets could be equal to 0. If the first bracket is equal to 0, p will be equal to negative a third. And if the second bracket is equal to 0, p will be equal to 5. Now if you just look back at your domain in the question, it told us that p was greater than 4. So therefore the only answer that is possible here is p equal to 5. So that is our final answer. So just now would be a good time to pause the video, take this down in your notes, and we've got one last example in this video. So let's take a look at example 4 now. We want to solve log to the base 2 of 7 equals log to the base 2 of x plus 3 for x being greater than 0. Now, at the moment, there doesn't appear to be much that I can do. One option might be to subtract my log to the base 2 of x from both sides, and then I would have the two logarithmic terms subtracting from each other, and I can then divide the arguments, and 7 over x would be equal to 3. But an alternative way, which is good to use, would be to express 3 in terms of log to the base 2. So remember, log to the base 2 of 2 is equal to 1. So actually we could express 3 as 3 log to the base 2 of 2. So that gives us the equation log to the base 2 of 7 equals log to the base 2 of x plus 3 log to the base 2 of 2. Now we can now see that 3 log to the base of 2 of 2, I can express that as log to the base 2 of 2 cubed. So that leaves me with log to the base 2 of 7 equals log to the base 2 of x plus log to the base 2 of 8. Now on the right hand side, I've got two logarithmic terms adding together, and they both have the same basis. So that means we can multiply the arguments. So log to the base 2 of 7 is equal to log to the base 2 of 8x. On both sides of this equation, I've got log terms with the same bases, so that means the arguments are equal to each other. So 7 is equal to 8x, and dividing throughout by 8 means that x is equal to 7/8. So just now it would be a good idea to pause the video before the screen goes blank, copy this example down in your notes, and then complete the assigned exercise for today until you're really comfortable solving logarithmic equations.